This is on the archive today, so if you're interested, please check it out or ask me questions. But yeah, I'm just basically going to be talking about this project because we just submitted it. So first of all, what is a theorist's view of what a BE X-ray binary is? It's a binary that contains a compact object, most often a neutron star, and a BE donor star. And as we've been discussing, as many of you know, BE stars are observed to be rapidly rotating, and this is believed to be linked to the formation of the decretion disk. And this is really important because the decretion disk in the system allows you to observe it as a BE star, first of all, and it leads to these periodic X-ray outbursts that we see from these systems, which allow us to characterize the compact object. Why are we interested? Well, it's a binary, and we're in the right place for that. But BE X-ray binaries make up a majority of all observed high mass X-ray binaries. So we have the largest sample of these rare objects in this subclass of HMXB. They have compact objects, so they're cool, and they go through binary cell evolution. So yeah, the standard formation scenario is that this rotation from the BE star is coming from a phase of Rocha-Lowenfeld mass transfer. If the system survives until the end of its life, the primary explodes in a supernova, which forms the compact object in this system. And so what you're left with is a rapidly rotating BE star and a compact object if it remains bound in the orbit. For this study, we're using Poseidon, which is a population synthesis code that's trying to merge the detailed binary evolution models in MESA within a population synthesis framework so that we can do statistics and population studies like this. Here I'm just showing a long list of individuals who are collaborating on this project. It's a big team that works on this. Monica and Meng, who are also here, are developers for Poseidon, and I've been doing development for the project since it started. So here I'm showing one of the binary evolution grids that we're using inside of Poseidon to model these Rocha-Lowenfeld mass transfer phases of evolution. Here I'm showing the log of the primary mass on the horizontal axis and initial orbital period on the vertical axis, and each point shows the initial conditions of one simulation. And the two panels are the same mass ratio, but on the right, we're showing sort of like the characteristic evolution outcome, and on the left is one continuous quantity, which is the surface rotation. And so because we're using MESA binary models, we can make some assumptions about how the rotational evolution of these systems evolves. And we're using this boosted wind, this like rotationally limited accretion formalism that we've been talking about. But we don't necessarily have to assume solid body rotation when we're in this binary model regime. So that's our data sets. We're trying to replace sort of the rapid prescription for mass transfer with the results of binary MESA calculations. How do we form this X-ray binary population to compare to the galactic sample? We start with some initial sampling of parameters. This is pretty standard in population synthesis. We sample some circular binaries with masses and orbital periods, and the initial rotation rates are assumed to be synchronized with the orbit. Then we use the results of the detailed binary MESA models to determine what the outcome of the evolution was for one of these systems. If the primary reaches the end of its life, we have to model the supernova. And then if the binary is still bound, then we have this compact object plus star configuration, generally eccentric, and we evolve this system in time. This is the phase of evolution that we're interested in studying to look at the BE X-ray binaries. Now, we have to do a lot more choices for all of the things that we think are important for BE X-ray binaries, including the lifetime of the system, what we decide in our models should be a BE donor. And because we're modeling rotation from the binary evolution models, we can make some statement about what the critical rotation should be above which the BE phenomenon occurs. Some donor mass constraints, and we need to model things like the disk size and the accretion rate to model the X-ray luminosities. But I'm not going to talk about this too much. If you're interested, please ask later. The main thing I want to get to is the results. So we have the log of the orbital period as a function of eccentricity, and this is the time sampled evolution of all the binaries in a compact object plus star configuration. So there's everything that survives mass transfer and survives the supernova. So it has a neutron star and a black hole, and these are the only cuts to the population. And so the general features I'm going to point out is these circular systems, and then you have these more like eccentric systems at the intermediate and then very wide orbital periods.
What is the grayscale again?
So we apply some time sampling to all of our binaries, and then to account for like the lifetime of the system, it's just the lifetime during that phase. And so each sample for the time evolving parameters like the mass and the orbital period eccentricity get a weighting that's proportional to the lifetime. And then, yeah, we apply our selection criteria for what are BE X-ray binaries, and we compare it to the galactic, a subset of the galactic sample of BE X-ray binaries. And this is one, iteration of a binary population synthesis physics, but it's nice that we know that BE stars are rapidly rotating, and we actually try and model this in MESA so we can see like, does the modeling that we have in MESA sort of hold up to this population? And we can ask sort of why are we getting this matching in period eccentricity space? We actually think that it's coming a lot from just the rotational evolution of these systems. So I'm showing a one-dimensional histogram of the rotational distribution of the donors, the donor masses, and the compact object masses and the eccentricity. But the difference between the green and the sort of pink line is that green is just if you said, give me everything that is only above 0.5 of critical, and you say like these things should appear as BE X-ray binaries, you kind of get the correct mass range-ish for BE type stars. You get the right compact object properties, and you also get the right eccentricity distribution. You kind of exclude circular systems. And we understand this through like the tidal circularization, essentially, of these systems, because if you circularize, you're necessarily synchronized. And then if you're synchronized in these orbits, it's very, very slow rotation. So if you cut on rotation, you actually avoid including circular systems in your sample. What's the time? Okay, so yeah, we're interested in the rotational evolution in this for these BE X-ray binaries and sort of tracking at different phases of evolution. So you can see the distribution at ZAMs as well as subcritical. This is sort of an imprint of the synchronized to the orbital period. After mass transfer, a lot of them get spun up to high fractions of their critical rotation. This is expected from the you accrete 10% and you basically get to critical, and then the boosted winds sort of reduce the rest of the mass. And then the time sampling, you kind of move this peak. It's like shifting to the left, and there's a distribution that goes to higher rotation rates. And this is the TAMS evolution on the main sequence, where the structure of the star is changing and the critical rotation velocity of those stars is decreasing, which causes the ratio of omega over megacrit to increase for some of these systems, and tides sort of like shift these back. And this is consistent with some observations of rotation rates for BE stars. Let me think. So yeah, here's a time series of one of the models that we were looking at, showing the masses of the primary and the secondary, and then the rotation rates for both of the components. And this is just showing that as case B mass transfer is initiated, the secondary spins up very quickly after accreting very little mass. Then the rest of the mass that's being transferred from the primary is lost through the boosted wind of the secondary. And then this system goes through a second case of case BB mass transfer from the stripped helium star after it evolves off its main sequence. And this is sort of characteristic of the population when we look at all of the B X-ray binaries in our population. And from this, we were able to calculate a mass transfer, an effective mass transfer efficiency. Given this rotationally limited accretion, we can basically just calculate how much is accreted versus how much is donated through these simulations. And then we can apply it to our astrophysical population. And so what we get is a mass transfer efficiency distribution given some assumption about the rotational evolution from the MESA simulations. So this is really exciting to me because it means we can change our physical assumptions about angular momentum transport, and we can get a different mass transfer efficiency distribution to look at instead of just a single number for our population. I think I'm running out of time. The last thing I'll mention is that we sort of were interested in the B phenomenon itself in this study. And what this plot is showing is the number ratio of black hole to neutron star B X-ray binaries. And it is sensitive as a function of what rotation rate you assume the B phenomenon is efficient. And it changes by orders of magnitude. And people have used this number to probe mass transfer physics or supernova physics, but we're showing that if you just change what you assume about the BE phenomenon, you can completely change your resulting distribution. So we're taking a harder look at BE X-ray binary modeling in PopSynth. So I think that's all I have time for. We have some self-consistent rotational modeling with one iteration of our physics, but it's the first time we can do this at a population level. Poseidon allows us to do these kinds of interesting population studies. And the B phenomenon, I think, is a leading uncertainty in future binary population synthesis studies that we have to wrangle with. And that's it. Thank you.
Hi, thank you for the great talk. Harai and Mendel looked at BE X-ray binaries and found that you need to be greater than roughly 90% Roche lobe filling in order to ignite the BE phenomenon. Have you looked into this, and do you think it would impact some of the wiggle room on your critical omega?
I'm not familiar with the reference to the Roche filling factor for the BE phenomenon.
Okay.
This is
It's for X-ray, not for B phenomenon.
BE X-ray binaries, yeah.
It's for black hole X-ray binaries. Black hole
both.
like I think I'm used to this for like wind accretion, but this is coming from accretion directly from a disk. And so, yeah, sorry, maybe I didn't define what the B phenomenon is. I mean like launching of a decretion disk around the donor star.
Okay, maybe I missed that. Okay.
Questions from an observer. What would you need to constrain the physics from the observations?
So at this point, I think the rotational distribution of BE stars in different environments would potentially be constraining. There's papers looking at the BE phenomenon. This is like BE versus BN stars. So these are BN stars are rapidly rotating, but they don't have disks. And they're looking at it as a function of evolutionary stage. Is it a function of mass? Is it a function of metallicity? If we can have better constraints on what the BE phenomenon is, we can forward model it and make some choices. But since we can't forward model it, this sort of very simple modeling paradigm, it impacts what the resulting population is. And if we don't have good models for this, then we're kind of stuck, I think. So if we have more data, if we can understand the BE phenomenon itself in more detail, and I think observations will help with this, then I think this would be a way forward.
actually about this diagram, which is neat. So what's the observed value? I guess it's uncertain. Yeah, but
yeah. So all of the sort of models that we see, we apply some luminosity thresholds, we apply a lifetime given the star formation, but the selection effects for these systems are notoriously very challenging to model. And so oftentimes for this, I mean, whether or not there has been a black hole detection of a B X-ray binary, it is unclear. And so the observational number is like, 10 to the -2 or something and below. Yeah. There's one claimed, but a recent paper sort of got a new orbital solution and throwing it into, yeah. So this number people have claimed is sensitive to the physics.
Okay, cool.
I just wanted to add another problem that we have with B stars. The B stars turn on and off, and they turn on and off very fast. So like, are you in any way trying to consider that no?
I think like this is as far as we got in the sense that this is a very simple choice that people usually make in BPS, and people change where this line is in their studies, like citing different papers that try and measure what the true rotation rate of B stars is. And this alone is enough to change your answer by orders of magnitude. I think this is scary. But yes, of course, we know observationally there's like duty cycles. And this is convolved with the X-ray luminosity duty cycles that people apply in just regular X-ray binary studies. So it's a big problem, I think.
I want to take chair's prerogative and do a very quick follow-up to what Tomer's question. Is the rate of which you form black holes or neutron stars is suspiciously metallicity, or at least for black holes, it's very metallicity dependent. And this is also what Flora in her paper showed with the yield of metallicity for binary neutron stars, or for neutron stars in general. It's very physics dependent, so it can vary by a few orders of magnitude. But yeah, gotta do what you gotta do. And then I think Kushik had a question.
Yeah, I had a question on the period eccentricity distribution. Can you go back to the period eccentricity plot?
This?
Yeah. So here, for all the observations, like, does none of them have like eccentricity of 0? Do I read that correctly?
As far as I understand, there's some very low systems, but sometimes people define BX-ray binaries as eccentric because there's no circular BX-ray binary observed, as far as I understand.
Doesn't that then make a bigger problem for us modelers? Like they undergo a case A or case B mass transfer, which should circularize the binary?
Yeah, there's a kick.
They get a kick in eccentric orbits, and then they're eccentric. But at least if you do the rotational cut on this population, you exclude the circular systems from tidal evolution.
And how kick dependent is the predictions from the models?
How what dependent?
Kick dependent, like the.
Oh, it's sensitive a little bit, like within standard PopSynth, but yeah, there's papers studying just the kicks effects on the BX-ray binaries, and they showed that within the range of parameters that people usually use, you get the same distribution unless you do something completely different. And so one of their main conclusions was like, yeah, the orbital period eccentricity sort of probes different physics than if you look at like the donor mass distribution or something else. So